YouTube, we've been discussing the quadratic formula, and in this video what I'm going to do is I'm going to mention this value of what we call the discriminant here. And so in the quadratic formula, which is this, this general solution for x if you have some standard form thing set equal to 0, we say x is always equal to this negative b squared plus or minus the square root of b squared minus 4ac all over 2a. Basically, this inner portion of the radical right here, this gets a name, or we give it a name at least. We refer to this as the discriminant, this b squared minus 4ac thing. And the reason why we pay so much attention to it is because, well, at least we were able to see in the last video that if what's inside of here is positive, what we get are two real answers, but if what's inside of there is negative, we're not going to get any real answers, you're going to get imaginaries. And what if what's inside here is 0? We actually get the same answer twice. So just by analyzing the value of b squared minus 4ac, the nice thing about this is we can determine the number and type of solutions that we're going to get before we even do all of this quadratic formula mess. So this core concept table you see here, it says analyzing the discriminant for some standard form thing set equal to 0. Basically what I want you to see here is this. Again, restating what I've already stated. If b squared minus 4ac, or the discriminant, if it's greater than 0, in other words, if it's positive, okay, then what we know is this. We're going to get two real solutions, and we have to have two x-intercepts for our graph because those are going to be those real solutions. What if b squared minus 4ac is 0? Well, again, if this is what's in here is 0, you're really going to get negative b over 2a and negative b over 2a. In other words, you're going to get one real solution, which is what this says right here. You're going to get one real solution. And in terms of where that would have to lie on our parabola, well, of course that would imply that the vertex of the parabola is the only part that is touching the x-axis. And then last but not least, if what we get in here is negative, okay, if we get a negative discriminant value, in other words, what's inside the radical is going to be negative, then we're going to get two imaginary solutions, or two imaginary roots of zeros. And this will have no real x-intercepts, so you can see that we've listed this here. So all I want to do in this video is basically analyze the discriminant for each of these three standard form equations set equal to 0, and then determine, well, then how many solutions would we get, and also what type of solution would we get, and we can refer to this graphic over here. So looking at this first one here, it looks like we have an a value of 25, a b value of negative 20, and a c value of 4. And again, recall that all I really am concerned with in this video is the value of the discriminant. And this is something we could always go look at first. We'd have not negative b, so used to using the quadratic formula here. We have b squared minus 4 times a, which is 25, and c, which is 4. So in this case, we're going to get 20 times 20 really is 400. Even if it's negative there, we'll still get a positive 400. And then 4 times 25 is 100. 100 times 4 is 400. In other words, look what we end up with here. What we would get inside the radical if we were to be using the quadratic formula on this is 0. And because the discriminant is 0, what we know is we're going to get one solution, and it's going to be real. And it would have to lie at the vertex in terms of its x-intercept here. Looking at the second example here, we have a, b, and c respectively look like 1, 2, and 6. So again, we're going to find the value of just the discriminant, just to talk about the number and nature of the roots. We have b squared, which is 2 squared, minus 4 times a times c, 1 and 6 respectively. So we're going to get, in this case, 4, and then this would be a negative here. It looks like 4 times 1 times 6 is 24. In other words, we get negative 20 would be inside the radical there. And so because this is negative, what we know is we're going to get two solutions. The only time we get one solution is if you get 0 inside for the discriminant value. But we're going to get two solutions, but the fact is they're going to be imaginary is what we wanted to kind of illustrate here, because we're going to end up taking the square root of a negative. And then last but not least, we say looking at this one, you might be able to foreshadow here that, oh, you think that this is an example of one that comes out to be real? Yeah, probably. But let's take a look regardless. We'd say, well, b squared minus 4 times a times c. We have a b value of 2, and then a value of 1, and a c value of negative 3. In this case, we get 4. Now, because of this negative 4 and this negative 3, there are two negatives here. This will actually come out to be positive, and 4 times 1 times 3 is 12, so we end up with 16. So if we were to solve this here, we would say because this is positive, we're going to get two roots, and they're actually going to both be real. So that is the nature of the discriminant and how we use it to kind of judge how many and of what type our roots are. Okay. So the last thing I want to leave with on this video before we get into application problems is essentially this. Up until now, we've solved a lot of quadratic equations. And the last thing we've been focusing on in this last series of videos is the quadratic formula. But what I want to kind of point out here is this. given that all of these other methods, graphing, using square roots, factoring, completing the square, they exist, and it's really convenient to use those in given situations, the thing I really want to point out here is that the quadratic formula can be used for any quadratic equation. The only stipulation is that it must be written like this. And I hope you realize that this is not always the most convenient way to do it, but if you have to fall back on something, this is the way to go. Cheers.